Hello, today we finish up our topic on integrals. We're going to be doing section 8.8, which is improper integrals. So far, the definite integrals you have seen. The definite integrals have been defined over a finite interval. And the interval we normally label a to b. And the integrals have been well behaved on these intervals. Then well behaved. So that just means they exist. They don't go off to infinity. No holes. Just everything continuous. So here we're going to talk about what happens if we remove those two conditions. What if the interval is defined over an infinite interval, and or what if the integrand, the function you're integrating, is not well behaved? What if it does go off to infinity? So a little bit of motivation to see how we're going to be dealing with these integrals. So consider the region. This region is infinite, bounded by f of x equals 1 over x squared for x bigger than or equal to 1. So that looks like this is 1 over x squared. That's bad drawing. Let's do this. Yeah. And then we're starting at 1. And I'm going to color this in yellow. It's light on purpose, but we want all of this region. We can't find this area directly. I mean, it's an infinite area. You can't figure out an infinite area directly. But what we can do is we can truncate this area. We're going to truncate it at x equals b. So the reason I made that hard to see was so that when I come here, you can actually see this. And we're going to find this area. So and find the corresponding area. This is doable. This is just a definite integral. So that's the integral from 1 to b of dx over x squared, which is negative 1 over x evaluated from 1 to b, which is negative 1 over b plus 1. Okay, so we have a formula for the area truncated at b. We can't just plug in b equals infinity, but if we let b go to infinity, then this would be the area we are interested in. So we get the area we want is the limit as b goes to infinity of negative 1 over b plus 1, which is just 1. Thus, the integral from 1 to infinity of dx over x squared, the way we did this is we said let's truncate this at b and then take the limit as b goes to infinity. And then that was 1. This is how we will deal with infinite limits of integration. Infinite. So I'm going to box it because this is kind of like the tactic is we write it as a limit of a truncated integral. So definition, we have two different types of improper integrals, and we're gonna look at the first one first. So integrals over unbounded intervals are improper integrals of type 1. So examples of these, we have the integral from a to infinity of f of x dx. The way we deal with this is exactly what I wrote above. We take the limit as b goes to infinity of a to b f of x dx. We can also have the integral from negative infinity to b of f of x dx. And here we do the same thing. Let a go to infinity, and then take the integral from negative a to b f of x dx. And then we could combine the two. So we could do the integral from negative infinity to infinity, so over the whole real line of f of x dx. And the way we do this is we truncate it at some point c. So we have the integral from negative infinity to c, plus the integral from c to infinity of f of x dx. And then we use 1 and 2. So since we are talking about infinity, and this is area under the curve, and we're taking the area under the curve over the whole real line, this area could always not exist. And so we're going to define more about what we mean by that. So if the limit exists, i.e. it exists and it's not infinity, then we say that the integral converges. And we define the value of the improper integral to be the limit. If the limit is not finite, we say that the integral diverges. And in this case, that means that the area under the curve is infinite. All right, let's do 2 examples to illustrate these tactics. The first example, I'm going to actually say this is a very special example. And very important. Highlighter. So this example, we're going to evaluate the integral from 1 to infinity of dx over x to the p for all values of p. And by, I mean, this is a special example that's important. I mean, it's going to come up frequently in the remainder of the course. So, solution. We want this for all values of p, so we're going to break this up into 2 cases. We have the case that we can use the power rule to integrate this, so that is p does not equal 1. And then we have the case that p equals 1, in which case we cannot use the power rule. So I'll do the case that p equals 1 first. So that's the integral from 1 to infinity of 1 over x dx. By definition of the improper integral, this is the limit as b goes to infinity of the integral from 1 to b of dx over x. This is the limit as b goes to infinity of the integral of 1 over x is natural log of x from 1 to b. This is the limit as b goes to infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0, so this is just natural log of b. And this is infinity. Natural log of b does grow. Okay, so that's p equals 1. So now we do p not equal to 1. So we have the integral from 1 to infinity of dx over x to the p. By definition, this is the limit as b goes to infinity of the integral from 1 to b. And we can write 1 over x to the p as x to the negative p dx. This is the limit as b goes to infinity of add 1 to the exponent, so that's x to the 1 minus p, divided by 1 minus p, divided by the exponent, evaluated from 1 to b. So this is why we had to consider p not equal to 1, so that we can actually divide by 1 minus p. This is the limit as b goes to infinity of 1 over 1 minus p times the quantity 1 over b to the p minus 1 minus 1. What is this? This has two values. So we have if p is greater than 1, and then if p is less than 1. So if p is greater than 1, then we have b to some positive exponent. B to some positive exponent, as b gets large, that's just going to go off to infinity. And then 1 over something going off to infinity is just 0. So we would get negative 1 over 1 minus p, which is generally written as 1 over p minus 1. But if p is less than 1, then p minus 1 is negative. So really this is b to some negative power, which would just be b, it's 1 over b to some negative power, which is b to some positive power. So as b gets large, this whole quantity will get large. In other words, that's infinity. So the integral from 1 to infinity of dx over x to the p is, it is either 1 over p minus 1 if p is greater than 1, or it is infinity if p does not, if p is less than or equal to 1. So in other words, it converges for p greater than 1, and it diverges everywhere else. That's the main thing to take away here. Okay, so that was a one-sided improper integral. Let's do that case 3, two-sided one. So let's evaluate the integral over the whole real line, so negative infinity to infinity, of dx over 1 plus x squared. Okay, solution. The way we do this is we break this up over into two integrals. So this is the integral from negative infinity to 0 of dx over 1 plus x squared, plus the integral from 0 to infinity of dx over 1 plus x squared. Now these are improper integrals, so we write them as the limit, in this case the limit as a goes to infinity, of the integral from negative a to 0 of dx over 1 plus x squared, plus the limit as b goes to infinity of the integral from 0 to b of dx over x squared plus 1. These are well-known integrals. This is the limit as a goes to infinity of tangent inverse of x, evaluated from negative a to 0, plus the limit as b goes to infinity of the integral from 0 to b. We're not doing the integral anymore because this is just tangent inverse of x, evaluated from 0 to b. All right, tangent, if you plug in 0, tangent inverse of 0 is asking for what value does tangent equal 0, and that is when sine equals 0 and cosine does not equal 0, and that is exactly at 0. So this is just the limit as a goes to infinity of 0 minus tangent inverse of negative a, plus the limit as b goes to infinity of tangent inverse of b minus 0. Okay, evaluating this limit, this is asking, you're saying that tangent inverse goes off to, of tangent inverse of negative infinity. So where does tangent approach negative infinity? And that is when sine is 1, sine is negative 1 to get the negative sign, and cosine is 0. That is exactly at negative pi over 2, and we still have the negative sign. And then same thing with the second one. Where does tangent equal infinity? And that's when sine is 1 and cosine is 0, which is at pi over 2. So this is just pi. So drawing what this means graphically. If we were to graph this function, it looks something like this. Drawn a little bit better. Yeah, that looks better. Where it's centered at 0. And so it's saying that this area where these tails go off to infinity is pi. So that means that these tails kind of have to level off at some point and start adding like negligible amounts of area. All right, so those are improper integrals of the first type. To deal with them, you just, wherever you see an infinity, replace it with the limit as b goes to infinity. So definition. What are the other types of definite improper integrals? So improper integrals of type 2 improper integrals of type 2 have the function become infinite at a point. And the point has to be within the interval of integration, or else we don't care. To evaluate these integrals, evaluate. We break the interval over the problem point. Okay, let's see an example of this. Easiest way to see what I mean. So evaluate the integral from negative 1 to 2 of dx over x. So it's very important to note that this is not equal to natural log absolute value of x evaluated from -1 to 2, which is natural log of 2. It would be minus natural log of 1, which would be 0. So this is not how you do this. It's very easy to look at this interval and go, oh, I can just immediately integrate it, I'll integrate it, done, and not think about the fact that it's improper. So always when you see definite integrals, you need to stop and ask yourself, is there something else going on here? So looking at this, you have 1 over x as your integrand. That is not defined at 0. And we are integrating over 0. 0 is in our interval, -1 to 2. So said differently, since 1 over x blows up at x equals 0, we break the interval over 0. So the integral from -1 to 2 of dx over x equals the integral from -1 to 0 of dx over x plus the integral from 0 to 2 of dx over x. And now we treat the problem point as if it is infinity. So by that I mean we now do limits. So this is the limit as a approaches 0 from the left, because we are coming at it from -1, of the integral from -1 to a dx over x, plus the limit as b approaches 0 from the right, of the integral from b to 2 of dx over x. This is the limit as a goes to 0 from the left of the natural log of absolute value of x, evaluated from -1 to 0. Sorry, not 0, a. Plus the limit as b goes to 0 from the right of the natural log of the absolute value of x, evaluated from b to 2. Okay, that is the limit as a goes to 0 from the left of natural log of a, minus the natural log of 1, which is 0, plus the natural log of 2, which is some value, minus the limit as b goes to 0 from the right of the natural log of b. And absolute values in places. So we have 2 problems here. Actually, we're fine with 1 problem. So because of this absolute value, recall that the natural log is not defined for negative values. So the natural log of a, as a goes to 0 from the left, would not be defined, but we have these absolute values, so that means we're fine. We're actually approaching it from the right, from positive values. And as you approach, okay, let's draw the graph of natural log. Recall that the graph of the natural log looks like this, which means that the limit as x goes to 0 from the right of natural log of x is -infinity. So that would be infinity plus the natural log of 2 minus infinity. I think I have those backwards. -infinity plus natural log of 2 plus infinity. And this is undefined. Recall, you learned this in L'Hopital's rule. Infinity minus infinity does not equal 0. Since this is undefined, we say that this diverges. And let's add some words here. Integral from -1 to 2 of dx over x diverges. Okay, so that's how you deal with improper integrals of type 2. But notice that a lot of the, like this one, it diverged, and we're just done. I mean, who cares? So a lot of times we're going to care more about whether an integral converges or diverges. Luckily, we have tests for those so that we don't have to sit down and integrate everything. So we have the direct comparison test. And this is for integrals. We will have another one of these that are not for integrals. If f of x, not f of x first, if 0 is less than or equal to f of x is less than or equal to g of x on some interval a to infinity, then if we have two cases, if the integral from a to infinity of g of x dx, if this converges, then so does the integral from a to infinity of f of x dx. So a quick little explanation as to why this is. Let's say we have a little chart. And then let's say g of x goes like this, and this is g of x, and it converges. That means that the area below this curve, all of this area, is finite. Well, f of x is less than g of x, which means that the area below f of x will have to be less than the area below g of x. But if the area below g of x is finite, then you have something less than a finite value. That means that that must also be finite. So therefore, it must converge. Let's not do blue. The second one, the integral from a to infinity, if the integral from a to infinity of f of x dx diverges, then so does the integral from a to infinity of g of x dx. And this has a similar story. So if you have f of x, and if the area below the curve is not finite, so it is infinite, then if you have a curve that lies above it, this will have a larger area, and it's larger than infinity, so it must also be infinity. Okay, let's see an example of this. So, example, does the integral from 2 to infinity of cosine squared x over x squared dx, does this converge? No, I don't care what it converges to if it does, I just want to know if it does converge. So we do not have to evaluate this integral. So if we want to use the direct comparison test, we need to bound this above or below by something that we know converges or diverges. So we just look at this and we just start seeing how can we bound it. So we know that cosine squared x is less than or equal to 1. The range of cosine x is -1 to 1. It's being squared, so we just know it's straight less than 1. So if we divide this, both sides of this inequality by x squared, we get cosine squared x is less than or equal to 1 over x squared. And this is true for all values of x, but we'll specify for x in our range or domain -2 to infinity. Okay, so we have bounded it by something. So now we need to know how does this function behave? How does this integral behave? Since the integral from 2 to infinity of dx over x squared, since this converges, why is this? This is because of the special example. Here we have p equals 2, which is greater than 1, therefore it converges. So by the direct comparison test, we know that the integral from 2 to infinity of cosine squared x over x squared dx must also converge. We bounded it above by something that does converge, so this must also converge. Okay, one more example. Does the integral from 3 to infinity of dx over x minus e to the negative x converge? So I'll let you work on this. I would recommend pausing it. See how far you can get. This one's a little bit tricky, so if you don't get it, that's fine. And then unpause and see how you did. Okay, so we want to compare this. So first thing we know, x is definitely bigger than or equal to x minus e to the negative x. E to the negative x is always positive, so we're subtracting off something from x. Take the reciprocal of both sides. When you do that, you have to flip the inequality. You get 1 over x is less than or equal to 1 over x minus e to the negative x. Okay, so we bounded this by something below. So hopefully 1 over x will diverge so that we can say this also diverges by the direct comparison test. We know that the integral from 1 to infinity of dx over x diverges. Here, this is p equals 1 with the special example. So the direct, let's not put it there, the direct comparison test says that the integral that we are interested in, 3 to infinity of dx over x minus e to the negative x, also diverges. Okay, we're almost done. Sometimes the direct comparison test does not work. For example, just imagine if this inequality was flipped. Then we would have this is less than something that diverges. That doesn't tell us anything. So we would move to the limit comparison test. Again, this is for integrals because we will see another limit comparison test for something that isn't an integral. So the limit comparison test says if the positive functions, so notice we must have positive functions here, f of x and g of x. If these are continuous on a to infinity, and if the limit as x goes to infinity of f of x over g of x equals L, let's put it this way, where L is positive and not infinite, then the integral from a to infinity of f of x dx and the integral from a to infinity of g of x dx, they both converge or they both diverge. So whatever one does, the other must do also. Short little blurb as to why that's true. You saw with the pictures that the only thing that this, whether it converges or diverges, cares about is the tail end. The fact that you can truncate the integral at some point, and then you have a finite integral that's going to be finite, We only care about the tail. So what this limit is saying is that the tail of f of x and g of x behaves the same. Might be off by a constant, but they behave basically the same. So then if one of these has a tail that doesn't behave nicely and makes it diverge, then the other one must also have a tail that makes it diverge. And likewise with convergence. If it behaves nice, the other one must behave nice. Okay, 2 examples, then we're done. So example number 1. Show that the integral from 1 to infinity of dx over 1 plus x squared converges. So notice with the last 2 examples, the previous 2, we always compared it to 1 over x to the p. We're going to keep doing that. So we are going to compare it to the integral from 1 to infinity of dx over x squared. Because that is basically what we have there. We have an x squared. That 1 isn't really going to do much for this integral. So this integral converges since p equals 2 is greater than 1. And since the limit as x goes to infinity of 1 plus x squared over x squared equals 1 over x squared plus 1. Oh, I need a limit. Limit as x goes to infinity of 1 over x squared plus 1. That is just 1, and 1 is both positive and not infinite. That means that the limit comparison test says the integral from 1 to infinity of dx over 1 plus x squared also converges. Okay, last example. Show that the integral from 1 to infinity of 1 minus e to the negative x over x dx diverges. So why don't you pause it and try to do this one yourself. Okay, so now that you heard my dogs go crazy, solution. We're going to compare it again to a 1 over x to the p integral, and we know that the integral from 1 to infinity of dx over x diverges because p equals 1. Then do your limit. The limit as x goes to infinity of 1 minus e to the negative x over x divided by 1 over x. And notice that's what we did over here. We did 1 over, but then the reciprocals are just going to cancel. So as you see, this is just the limit as x goes to infinity of x over 1 minus e to the x, which is just the limit as x goes to infinity of 1 minus e to the negative x, which is 1. So the integral from 1 to infinity of 1 minus e to the negative x over x dx also diverges. And that finishes section 8.8.